Hey guys, welcome back. We're starting our second topic in our new unit of bivariate data. So we're looking at the associations between two variables whenever they're plotted across a scatter plot. So one of the things we're going to look in today is the relationship between horsepower and miles per gallon. And if you're familiar with physics, power is the rate of consumption of energy, right? And miles per gallon is essentially well, how many miles you can go per gallon, right? So if we're talking about how quickly we can consume energy, that's power. So horsepower is literally directly opposed to miles per gallon. And so we should not be surprised whenever vehicles with high horsepower also have very low miles per gallon. So anyway, kind of interesting looking at the difference between those kind of vehicles. So let's first look just a quick review of what we talked about yesterday. So here we have the association between the drop height of a roller coaster and the speed, and we expect a positive linear association between that. So the direction on this one would be positive. As the explanatory variable increases, so does the response variable. On interest rates and total mortgages, those are inversely related to each other, just like how we would expect the horsepower miles per gallon to be. So this would be a negative association between the two. As the interest rates increase, the total number of mortgages that they sell in millions or millions of dollars that they loan for mortgages is going to decrease. Shoe size and ACT scores. So as we would expect, there's no real association between your shoe size and how well you do on the ACT. So there would be no direction or neither in that one. We also describe association by their form. So this would be a linear form, which is pretty common. Then we also have curved forms. So this could be exponential. Keep in mind that they could be curved going up or curved going down, or they could be sinusoidal going up and down. It could be like parabola where it's like upside down, or a U shape going up. Lots of different things. And over here we have no form or no pattern. Describe an association by direction, form, and then strength. So this would be strong. And keep in mind, it does not have to be linear for it to be a strong association. It could be curved and still a very strong association. So this is curved as well, but it would be like moderate or moderately strong association. Then over here, we have a weak association. It looks like there might be some association over here because there's nothing in the bottom here. So it is a negative association, but it's a weak one. All right, then when the association is linear and there's no outliers and we're dealing with quantitative data, those are our three conditions that we have to have in order to calculate the correlation coefficient. Then we can calculate a correlation coefficient, which is the R, which I'm going to show you how that's calculated today. We're actually going to do it kind of by hand in the calculator, so make sure you have your calculator on hand. Today will be really important to follow along with the calculator. Because there's a setting we have to turn on, otherwise you won't be able to do any of the work moving forward. So is the number that measures the strength and the direction of the linear association between two quantitative variables. So -1 is the strongest negative correlation we could have, and a strongest positive correlation is going to be +1. So anything from -1 to +1, those are going to be the possible correlation coefficients. -1 would be a perfect negative association. So that would be if they were all like perfectly in line. +1 would be if they were perfectly in line over here, and then 0 would be somewhere in the middle. Remember, this is not like there's no like set rules on where the barriers are, like the left fence or right fence rules or anything like that. For a weak association, moderately strong association, very strong, perfect. Okay, so there's no like given rules, but this is kind of a scale of what kind of how I have seen it, how I describe it. But there's room for interpretation in there, I guess. All right, so conditions for correlation. So linearity, outliers, and quantitative. So first of all, we can't calculate correlation if it's not linear. So over here, if we calculate correlation coefficient of this curve data, we're actually going to get something very close to 0, and I'm going to show you why today. So don't even calculate correlation coefficient. It is only the measurement of strength for a linear association. So it's only appropriate when it's linear. If it's curved, it doesn't measure the strength of the association. Okay, so it has to be linear before we can calculate correlation coefficient. Oh, by the way, the word association is used for all types, including curved graphs. Okay, but when it's a linear association, then we use the word correlation. Correlation is just a special kind of association when it's linear. Okay, and the correlation coefficient is a special number or coefficient that we use for linear associations. Okay. All right, so it has to be linear. We have to make sure there's no outliers, because outliers can skew our z-scores and end up causing us to have much stronger association than we actually really do. And we have to make sure we're dealing with quantitative data, okay? In fact, you can't graph categorical data at all with a scatter plot. It has to be quantitative. So that's really for all scatter plots. But anyway, and correlation coefficients unitless. It's based on z-scores, and z-scores are in units of standard deviations. So there is really there's no units associated to a correlation coefficient. It's kind of cool. So this one would have a very high correlation coefficient because it's measuring the strength of linear, and it would be negative. So about should be about negative 0.5. It seems I never did fix that. I did the same thing yesterday. And then over here, it would be close to 0, and I'll show you why. So it's not appropriate to use the correlation coefficient to try to quantify the strength of the association of a exponential or a curved one. Okay, so what about this one? It's going to be negative, moderately strong, maybe close to negative 0.9. Yeah, okay, not bad. This one is also going to be, but this is curved, right? So this is not going to be a very good representation. So if this was linear with this amount of spread, right, then I would say maybe about 0.8, 0.85. But because it's curved, it's actually going to show less than that. So it's going to be about 0.73. Okay, kind of cool. And then over here, this is no pattern, so it's going to be close to 0. And in fact, it was a slightly negative, I guess, because there's some more lining up this way than there are that way. Oh no, but it's so close to 0 that there's no association. It doesn't matter if it's negative. All right, so here we can compare height versus weight. Oh, this is not comparing height and weight. I'm sorry. So just ignore that. Let me just delete that. Okay, so we are comparing brain size, like literally how big your brain is, with your IQ, performance IQ. So why somebody decided to do this, I don't know. It's kind of funny. So if you have a larger head or a larger brain, I suppose, does that mean that you're smarter? So our explanatory variable here is going to be brain size. We want to see how does IQ measure across brain size. So brain size is the part that you don't have control over, and then where we're expecting all the variation and response to the explanatory variable would be the performance IQ. So if we look here, it doesn't really look like there's a whole lot of a pattern. I do notice a big gap here. So with the larger brains, there weren't a lot of people that had below average IQ. So maybe there is something between brain size and IQ, but I have a really small head, so I don't know. The only thing I stick in my brain is a bunch of math, so everything else kind of gets pushed to the side. All right, so grip strength versus age. So as you age, what do we expect to happen with your grip strength? And then again, we have to pick the explanatory and the response variable. Anything that has to do with time is automatically going to be our explanatory variable. So we're seeing how does your grip strength change over time. Now on this one, we expect younger people to have a weaker grip strength, and then as you get older, it's going to go back down again. So I thought it might look something like this. So as you develop in 18, it gets really strong, and then somewhere late 60s or 70s. I shouldn't say that because if I arm wrestle my dad who's 65, he still wins, and I'm in the prime of my life. But that's because he like threw hay bales for his childhood, and I've stayed inside. So anyway, I can't make fun of him, but eventually I will be able to beat him, but it'll probably be many, many years before that happens. Anyway, so this is what I would expect to happen in that one. But again, this is totally up to interpretation. We don't have the actual data, so I don't know what it's going to be. All right, mountain climbing. So as your altitude increases, so as you climb in elevation, what's going to happen to the temperature? Well, as we get higher in elevation, the air gets thinner and actually gets colder. We get further away from the surface, and I don't know, and the radiation of the sun. I know you're more likely to get sunburns up there, but for some reason it's colder in higher altitudes. I should know that one. But anyway, so we're saying as the altitude changes, that's going to be our explanatory variable. We want to see the response variable, which is what we're measuring, is the temperature. So I thought it might look something like this. So when we're in low altitudes, so that's close to sea level, temperature is going to be higher, and as we ascend, it's going to get colder. Notice there is still some variation because there's going to be variation, I don't know, as the temperature changes naturally. Even if you stayed at one elevation, the temperature is going to change throughout the day. So whatever's going on, clouds, no clouds, wind, some stuff like that. So there's going to be variation, but it is going to be a pretty strong association. If we did it at the same time, we measured all the temperature just directly above where we're at, like with a, I don't know, with a weather balloon or something, we just, it ascended really, really fast, just going straight up. It would be very, very close to linear, I think. I could be wrong. I don't know. I'm just guessing. All right, so another thing we need to get into again is scaling. So this is going to be really important again. And we did have some questions about difference between scaling and shifting. So shifting, we shift things left and right. It changes everything except measurements of spread because it's not more spread out. It's just being shifted to the left or to the right. But for scaling, like if we're looking at the weight of, I don't know, 100 American males, and we measure them in kilos and then we measure them in pounds, the scale factor from a kilo is about 2.205 pounds. So all the data is just going to be multiplied by a scale factor. It's going to be scaled by 2.205. So the right fence is going to be 2.205. The maximum is going to be multiplied by that coefficient. The minimum is going to be that much higher. Everything, including the measurement of the spread, because all the data is going to be spread out by a scale factor of 2.205. So hopefully this graphic really captures what's going on when we scale something. And by the way, we could also scale something by something less than 1, where we're dividing by 2.205, for instance, and we could go back the other direction. So it does go both ways. Notice our minimum gets multiplied by our scale factor. Okay, that's cool. So does all the other measurements for like the individual metrics, like minimum, Q1, median, Q3, but the 5-number summary, okay? Then the measurements of spread, like IQR, standard deviation, and range, they're also going to be spread out by the scale factor of 2.205. These are what do not change when we shift something, okay, but everything changes when we scale it. So make sure you understand that. It's really important. So here we have 2 different scatter plots for the heights and the weights of these 100 American men. Okay, now this is done in centimeters and kilos. Okay, so this is height and weight in basically kilos and centimeters. And over here we do it in inches and in pounds. And if you look, it's the exact same distribution, the exact same scatter plot. The only thing that's changing is our X scale and our Y scale are now going to be multiplied by their respective scale factors. So whatever 30 divided by 12 or whatever for centimeters to inches, and then the same thing from kilos to pounds, which we said was 2.205. Okay, so notice it's the same scatter plot, the same association, the same strength. Doesn't matter what units we're using. When we calculate the correlation coefficient, we're going to be dividing by the standard deviation of those units, which is going to make them unitless, and it's going to give us basically just a scatter plot, and that's what allows us to compare them, which is actually really fascinating. So what's happening when we calculate correlation coefficients? So let me try to explain it this way. So if we collapse this, and right now this is a scatter plot which shows how the individual data points, kind of like in the contingency table, are spread across 2 variables. Our X variable is going to be height, our Y variable is the weight, okay? So all these points, they represent, if we just looked vertically going straight up and down, if we collapse these points here, it would fill in this bell curve. Do you see that? Okay, and if we collapse them horizontally, it would fill in this bell curve over here with this far outlier up top. Okay, so we're taking 2 variables and across 2 different distributions and spreading it out on the scatter plot, which is really, really cool. So what we're going to do is we're going to take the heights and the weights, and we're going to standardize those scores. So we're going to find the average height and the average weight, and that's going to be this point right here, the mean point, okay, which I think is about right here. I should graph it out. I'll do it in later days, but anyway. And then what we're graphing is the z-scores. So we have 1 standard deviation, which goes to here, another standard deviation, 2 standard deviations, and the same thing on the other side. This one should be, it doesn't like, it likes to rotate those for some reason, unless I redo the snipping tool. But anyway, and then here we have the other one, which would capture all of them going horizontally, and then here we have them capturing them all going vertically, essentially, is what's going on. All right, so we have our z-scores to 2, 1, and these are the z-scores for the height, and then the z-scores for the weight spread out here. And in the middle, that's the z-score of 0, 0, which is 0 standard deviations from the mean for height, and 0 standard deviations from the mean for the weight. So that's the 0, 0 point, okay, which is the mean. So average weight, average height, and that's going to be in the very center. And all of these others are going to be plotted coordinates of the z-score for their weight and the z-score for their height. That's like the x and the y points that are being plotted here. So this is called a standardized scatter plot, and this is just whatever the zoom stat gave us because it has to stretch it out. Anyway, so standardized stat plot, we use the standardized stat plot to calculate the correlation coefficient. So let me go to the next one. So this is the same thing. We just have an outlier up here. Let me go here. All right, so what we're going to do, this is how we calculate the correlation coefficient. It's the sum of the product of the z-scores divided by n minus 1, okay? So we're going to take the sigma, which is the sum of the product of these two z-scores. So like this point right here would have a z-score, this is 2 and 1.75. So we would take 2 times 1.75, which would be 3.5, and then we would add that, the product of that z-score, to the product of this one, which is 1.75 times 2.5, which would be whatever that value is. So we're going to multiply the product of each one of these z-scores, the x times the y, add them together and divide it by the n minus 1. Okay, all these green dots are going to be positive values because in this quadrant here we have a positive and a positive. Okay. And then same thing over here on the bottom, but now we have a negative and a negative, right? Because that's how all that stuff works. I'm trying to do this on the fly. I should have done it before, but that's okay. But when we multiply the product of two negatives, they become positive again. So anything that's going in these directions here in the first or the third quadrant are going to result in a positive product of a z-score. Anything that's in the second quadrant and the fourth quadrant would be a negative z-score, okay? And that's why positive correlations go in this direction and negative ones go in this direction, because they have more negative than the positive or whatever. Anything on the blue lines, which are going to have an average weight or an average height, are going to be a 0 for one of the z-scores, and so they're going to they're going to be neither positive nor negative, right? So we just call them non-negative, I think is the technical term. And when we add them up, they actually don't help or hurt the positive or the negative, but they do kind of lower. If we had a bunch of them that were lined up on the average, it would lower the actual overall strength of the correlation, because the magnitude would be lower, but it's not going to help the positive or negative. So this one clearly is going to be positive because we have much more green dots than we do the fuchsia or whatever color that is. All right, so anyway, really cool formula. That's how it works. And by the way, this outlier up here, it's going to be 5 and 1. So this value was like 3.5, right? This one is 5. So outliers themselves, because it's so far, 5 standard deviations is absurd. That's like crazy far out there, very unusual. Anything beyond 3 would be considered very unusual. So this outlier could be inflating and giving us a much higher correlation coefficient than what we actually would really have if we remove that point. Okay, so this is basically breaking down. We have our x for the x value of 0.2, the y value, z-score of 1.9, which would give us a product of the z-scores of 1 or 0.38. Okay, that's what I'm doing here. And then here we have 0.8 and 1, which would be 0.8. Both of those are positive. We'd add all of these products together with all of these negative ones. And if you notice, the positive ones over here and the negative ones over there, and they're kind of mirrored, like symmetric across both sides, they're going to cancel each other out, right? And the positive ones down here are going to cancel out with the negative ones down here. So when we add all these together, they're going to all add up to a sum of the product of the z-scores to be about 0. And then when you divide that, by the number of points we have minus 1, that's why this would give us a correlation coefficient of something which is equal to 0, even though that's not actually measuring the strength of the association, because it is a fairly strong association. It's just not linear. And that's why we can only calculate the correlation coefficient if we have a linear association. So fascinating stuff. All right, and here's another example, just kind of a warning. So population of Oldenburg, Germany at year's end versus the number of storks observed each year. So from 1930 to 1936, they saw as the number of storks grew, the population grew in this town of Oldenburg, Germany. So this is modern day Oldenburg, Germany. That's not the 1930s, but anyway, in the 1930s, they did a scatter plot. And so the question is, does it mean that when there's more storks in the area, that means more storks are bringing more babies? I don't know if you saw that movie, but it was decent. But it's funny because that's where babies come from, right, guys? So, so anyway, so as we have more storks in the area, we had more babies being delivered by storks. Oh my goodness, this is crazy. So we have to be very, very careful, because just because there's an association, or in this case, a correlation, which is a linear association, right? So just because there's a correlation between the number of storks and the population in thousands does not mean that there's a causal relationship between the two. We cannot conclude that storks were the ones delivering these babies. Instead, what was actually happening is it was actually the other way around. So as the population was growing, there was more habitation for the storks because they were nesting on the chimneys. So as they built more, as their population grew and the families were growing, they were having more babies, they were building more houses and more chimneys, and so therefore the storks were able to expand because they also now had more population. So kind of funny, thought you might enjoy that. So just a warning between correlation and causation. All right, 20 minutes. That's not too bad considering we went over some really important stuff. Let's go ahead and start on 37. So you're going to need your graphing calculator if you'll get that out for me. So here are the advertised horsepower ratings and expected gas mileage for several 2010 vehicles. Make a scatter plot for these data. So here's the data over here on the right. You have it on your piece of paper, so I don't have to worry about covering it up. I'm going to put it in list 1 and list 2. So if your lists are, if you want to clear your list out, one way you can do that is by going to second memory and then do the fourth option to clear all lists. Now I'm not going to hit enter because I don't want to have to put all that in, because that would take a ton of time. I would just pause the video and then resume it, but it doesn't matter. So go to stat and then edit. For list 1, we're going to put our explanatory variable, which is going to be the horsepower. And then in list 2, we're going to put the miles per gallon, and we should have in both of them 15 in each list. Okay, make sure you don't have any typos there. Then the next thing we want to do is graph a scatter plot. So we're going to go to second y equals, and make sure you just have one of them on. The scatter plot's the first one there, and we're going to go from list 1. So, so second here, and go down. So I'm going to hit second 1 to do list 1, and then second 2 to do list 2. And then I like the plus signs because they're easy to see, but they're also precise instead of the dots. I think those are kind of sloppy, but you can do whatever you like. And then hit zoom 9. Okay, and that's going to be our scatter plot. So you can go ahead and graph that out. It can be rough. It doesn't have to match exactly. And then you'll want to label the axes. So here on the bottom we have miles per gallon. Try this again. Okay, yeah. So miles per gallon, and then over here, nope, I did that backwards. So this would be horsepower, and over here we have miles per gallon. All right, and these are for vehicles from 2010. Describe the direction, form, and strength. So it's negative, right? So there's an inverse relationship between those two. So as we increase in horsepower, our mile per gallon is going to go down. So it's negative. I would say it's a moderately strong association, and it is linear. So you could say a moderately strong correlation. Find the correlation between horsepower and miles per gallon. So we want to calculate the correlation coefficient. Let me show you how to do that. I have to run a linear regression. So I'm going to go stat calculate linear regression, the fourth option, which is just fine. And X list and Y list is exactly the same. Storing regression EQ, we're not going to do that until the next chapter, but that will become important later. Then we're going to hit calculate. Now, when I did mine, it gave me the R, which is the correlation coefficient. Your calculator doesn't do it because I reset all the memory. So we have to turn the diagnostics on again. So what we want to do, let me show you how to fix that. All right, so we want to go to the catalog, which is the blue one here. So we're going to go second 0, which is the catalog, arrow down to diagnostics on. So diagnostics on, then hit enter. Okay, that'll turn on the diagnostics. So once you do this, after you've reset, like totally reset everything, like I installed new operating systems on the calculator, so I did an update. That's what happened. Once you do that, you won't have to do it again. So then you can arrow back up to linear regression, and we're gonna hit enter, and now you should get the R squared and the R here. So the R is going to be your correlation coefficient. The R squared is the coefficient of determination, which is pretty awesome. What that tells us is, I guess I'll go ahead and tell you, even though you don't need to know it right now, but 82% of the variation in miles per gallon can be accounted for by the variation in horsepower. So if we took horsepower out of the equation, 82% of all the variation of what we get in miles per gallon would no longer be there. So there would only be 18% or 17.4% of all the variation in miles per gallon left over after we account for the amount of horsepower that we have. So it's pretty stinking cool. It's called a coefficient of determination. It's got like a really awesome name to it as well. I think so, at least. All right. So next thing I'm going to show you is how we actually can do z-scores. I think I'm actually going to break that down into a separate video, just so this one is not so long, but I think you guys will enjoy that. So that's the table for it, and I'm going to explain it in a separate video. So let's look at number 22, because I don't want to go over 30 minutes if I don't have to. A study in traffic delays, 68 U.S. cities found following relationship between total delays and total hours and mean highway speed. Is it appropriate to summarize the strength of the association with correlation, meaning the correlation coefficient? Well, there are three things we have to check first. Conditions. So first, it has to be linear. Is this linear? Well, you might be able to argue this is linear, but this is not. This is all over the place, right? We can't have any outliers. These are clearly outliers. They're far away from the rest of the data. So that's going to inflate our correlation coefficient and to something that it's not supposed to be. And then also we have to have quantitative data. Both of these are quantitative with their units and everything, so we're fine. But the two problems we have is it's not a linear association in the first place, and we have outliers. So is it appropriate? No, because the association is not linear, and it's not, and we have outliers. So we cannot calculate the correlation. We cannot measure the strength of the association using correlation, because correlation is only for linear and without outliers. All right, 24. A researcher investigating association between two variables collected some data and was surprised when he calculated the correlation. He had expected to find a fairly strong association, yet the correlation was near zero. Discouraged, he didn't even bother to make a scatter plot. Explain to him how a scatter plot could reveal the strength of the association that he anticipated. Well, if it wasn't curved, so if it wasn't linear, then we wouldn't be able to use the correlation to measure the strength of the association in the first place. So if it was curved like we have here, this is still a very strong association, but it would have given us a correlation of zero. So that could have been what happened for him. So what he needs to do, first thing, before you calculate correlation coefficient, is you have to graph the scatter plot to make sure we don't have outliers and to make sure it's linear in the first place. And if it's curved, some things we can learn, and we will learn how to do, is we can actually straighten out the data by re-expressing it to make it more linear in our model, and then we can calculate the correlation coefficient, which is pretty stinking awesome. But we'll do that in later units to come, or later chapters to come. So anyway, that is why you should always graph the scatter plot to make sure it's appropriate to calculate the correlation, because the correlation only measures the strength of a linear association, and if it's curved, then it won't help you. All right, so just under 30 minutes. I'm going to make a separate video to show you guys the ins and the outs of how we calculate and how the correlation coefficient is calculated. I think you're going to enjoy it. So I'll see you guys later. Have a good weekend.